So we're going to begin by talking about the method that we will use to find these initial conditions. Now, as a reminder, for first order circuits, we found two of these conditions. The first was the initial condition, which was at T0 plus, and that was either the voltage across the capacitor or the current through the inductor. Now, of course, we actually drew it for time less than zero, but because of the voltage continuity concept for a capacitor or current continuity concept for an inductor, drawing it for time less than zero let us know what it was at zero minus, which has to be the same as what it is at time zero plus. So these are the two things we found for first order circuits, no matter what we were asked to find. If you were asked to find the voltage across some random resistor and there was a capacitor in the circuit, you would ignore what you were asked to find. You'd find the voltage across the capacitor at time equals zero. You'd also draw it for time equals infinity and find the voltage across the capacitor then. Or if the circuit had an inductor, you'd find the current through the inductor at time equals infinity. And only as a very last step, after you solved for the voltage across the capacitor for all time, or the current through the inductor for all time, would you finally find what you're actually asked to find. That's different than in second order circuits. In second order circuits, the goal is at time equals zero plus to find whatever you're asked to find, whether it's a current or a voltage, and whether it's has to do with a capacitor, a resistor, an inductor, anything. I'm just going to call that X. You're going to find whatever you were asked to find at zero plus. And then you'll find the derivative of whatever you were asked to find at zero plus. And then over at time equals infinity, you'll find the non-derivative of whatever you're asked to find at infinity. So just to make that correct, if you were asked to find the voltage across a resistor, you would find the voltage across the resistor at zero plus, the time derivative of the voltage across the resistor at zero plus, and the voltage across the resistor at time equals infinity. And those would be the initial conditions. This would be the final condition. So this is the overall goal, and we're going to need to find these things with a number of substeps. So let's talk about that. So the method to find second order initial conditions and final conditions is this. I'm not going to talk much about the final conditions because the final condition here is the same as it was for first order. You draw to time equals infinity, capacitors are open, inductors are short, and you can find it directly, whatever you're asked to find. I'm going to spend most of my time talking about how to find these guys here because this is different. So there's a few steps to find these second order initial conditions. Our goal is we want to know what is V C naught and I L naught. And I know that seems to fly in the face of what I just said up here, that you don't care about VC or IL. You want to find whatever you're asked to find. But our first step in that is to find VC naught and IL naught. And to do that, we have to draw it for time less than zero. And because it's time less than zero, we are in DC steady state. And because we're in DC steady state, we don't have capacitors. They look like opens with a voltage across them. And that voltage across them is defined to be VC naught. Similarly, we've got inductors that look like wires, and they've got a current going through them, which is IL naught. And those are the two things we need to find right up here. Those are our goal things to find. Also, we've got no switches. They're either open or closed. We don't have any U of T sources. They're all evaluated. They're all either 0 or 1, depending upon if it's a U of T or a U of minus T. And so then you use your circuits 1 skills to find VC naught or IL naught. Okay, that much seems just like first order circuits, with the exception that in first order circuits, you found VC naught or IL naught. You didn't have both capacitors and inductors, and now you're finding two things. The second step is brand new. We have never seen anything quite like it before. And for that, our goal is to find the requested value. So I'm going to call this X. And you know that that's going to be whatever you're asked to find. V of R, I of R, anything. Your goal is to find X at 0 plus and the derivative of X at 0 plus. And just to make it concrete, let's say we want to find V sub R at 0 plus and therefore be V sub R prime also at 0 plus as an example. Okay. So in order to do that, you're going to have to redraw it at t equals 0 plus. So unlike anything you did before with first order, this is at an instant of time. It is not over a region of time. So at that region of time, we know what that capacitor looks like. Because you know what the voltage is across the capacitor, you found it for time less than 0 in step 1. And since the voltage across the capacitor cannot change instantaneously, you know exactly what that voltage has to be at time equals 0 plus. And since you know what that voltage has to be, the capacitor now looks like a voltage source, a value VC naught. Similarly, that inductor looks like a known current source, a value I L naught. And it's important to use passive sign convention if you define any extra things around it. So for instance, if we're defining the current going down, then you have to define using passive sign convention the voltage across that inductor like this. Because again, it's not really a current source, it's really an inductor. Similarly, you have to define the current through the capacitor like this, using passive sign convention because it's truly not a voltage source, it's truly a capacitance. It's just a capacitance whose voltage we happen to know, so it's easier to represent it as a voltage source. Now, once again, there should be no switches at 0 plus. They're all open or closed. There should be no U of T's. They're all evaluated at 0 plus. And then you find the requested X at 0 plus. So for this example, we'll say, find the voltage across the R at 0 plus. Now that shouldn't be hard to do. It looks just like a DC circuit. You just have a extra voltage source or an extra current source. You can find that. What is different is when your goal, your next goal, which is to find X prime of 0 plus. So perhaps I got a little ahead of myself over here when I said find both those things. I'm going to break that out. So as an example, we want to find V sub R at 0 plus prime. Now you're not going to redraw your circuit. This is still at time equals 0 plus. And in that circuit, you should be able to find the voltages across every component, and you should be able to find the currents through every component. So you know what the voltages and the currents are everywhere, but you're asked to find derivatives, and that's something new. To go from regular currents and voltages to the derivatives of currents and voltages, you will always use these two laws. You know that the voltage across an inductor is equal to the inductance times the derivative of the current through it. So the derivative of the current has got to be 1 over L times the voltage across it. But you just found all of the voltages across all the components. So therefore, you can now find this first derivative value. Similarly, you know that I equals C dV dt. And so you can solve for VC prime. It's just equal to 1 over C times I sub c. And again, you just found from step 2 all of the voltages and all of the currents everywhere. So you've found the current through that capacitor. So plug it into this equation, and now you've found 2 derivative values, I sub L prime and V sub C prime. Now, you will always use these equations because these are what will let you transform from the non-derivative world into the derivative world. If what you're asked to find happens to be I sub L or V sub C, congratulations, you're done. You've now found I sub L in step 2 and I sub L prime in step 3, and you can drop the chalk and walk away. If, though, you're asked to find something else other than I sub L or V sub C, you've got to use extra steps. You still definitely use these, but you might also have to use some other rules too. Now, you already know Ohm's law. If Ohm's law is true, and it is, then the derivative has to be true too. R is a constant, so we don't need to take its derivative. So this is a way that if you happen to have a resistor in series with an inductor, and you're asked to find, say, the V sub R, as we started talking about as our initial example, using your step 2, you can find V sub L for time equals 0 plus. Then, now that you know V sub L at 0 plus, you can find I sub L prime at 0 plus. It's just 1 over L times V sub L at 0 plus by this equation. So you found this first, then you found I sub L, and now that you know I sub L prime, you can say that I sub R in this circuit has got to be the same as I sub L, right? Whatever current goes to the top has to go through the bottom. And therefore, the derivatives, take the derivative of that equation. The derivative of I sub R has to be equal to the derivative of I sub L. And therefore, by Ohm's law over here, V sub R prime has to be equal to R times I sub R derivative. And now you found this, because that's a function of I sub R prime, which you found up here, which is a function of I sub L prime, which you found here, which is a function of V sub L prime, which you found all the way back in step 2. So big picture again, you're going to use these 2 rules to change from the world of non-derivatives to derivatives. And then you're going to use things like Ohm's law here to find the particular derivative value if it's not I sub L or V sub C prime. Here's another one that you'll see often. You know that I1 plus I2 is 0 from KCL. 2 currents are going into it. Some of the currents have to be equal to 0. The derivative of the first current plus the derivative of the second current has to be equal. Similarly, KVL says that if you have a mesh, the sum of the voltages around the mesh have to be 0. So take the derivative of that equation. The sum of the derivatives of the voltages have to be equal to 0. So as an example of why you might find this second rule, this KVL rule, useful, let's see about a larger circuit out here. Let's say this is equal to a constant 10 volts for all time less than 0 and time greater than 0. Maybe it's even more complicated than that. Maybe it's got more stuff over here and more stuff over here. Let's say we're asked to find what is the voltage across the inductor. That's something new. And if we find that, it's not hard to find V sub L at 0 plus. That's step 2. We've done that before. But it means we also must find V sub L prime at 0 plus. And the first thing we do is go back to these rules that we always use, and we hope to find a V sub L prime, and we don't. So we're going to have to pull that out some other way. And a way that we can pull it out is to do a KVL around here. And when we do that KVL, we find that it's plus 10 minus V sub L minus V sub R, and all that equals 0. And there's our KVL. And if that's true, the derivative has to be true too. So if we take its derivative, the derivative of a constant is 0. The derivative of minus VL is minus VL prime. And the derivative of minus VR is minus VR prime. So therefore, that V sub L prime that we're trying to find is equal to just minus VR prime. I just solved this equation for V sub L prime. And we already found V sub R prime down here. So this would just be what we get from here. And now from all these steps, we can find our V sub L prime, which is what we need to find if we're asked for V sub L. So this is why, big picture again, it's important to keep track of what you're asked to find. If you were asked to find for a particular circuit, I sub L prime, you wouldn't need to do any of this. You'd look at this circuit, you'd jump over to these always use equations, you'd find I sub L prime directly from the voltage across it, and you'd be done. But here clearly, while I sub L prime is pretty easy to find, I sub R prime requires 1 extra step, V sub R prime requires 2 extra steps, and V sub L prime requires 3 extra steps. But they're no more complicated than just simply applying Ohm's law, KCL, and KVL. Those are the only 3 rules you'll need, and applying their derivative versions. The last step is to find not the initial conditions, but the final conditions. And so for that, the goal is to find X at infinity. Continuing on with our example, there'd be V sub R at time equals infinity. And I'm not going to spend time doing that. It's the exact same thing as we did in first order equations. You draw the circuit at t equals infinity. And that means we're going to be in DC steady state because nothing is changing at times infinity. So capacitors become opens, inductors become shorts. And now you find directly whatever you're asked to find. Not VC, not IL at infinity, but you're asked to find whatever you're asked to find, which, as our example, would be that V sub R. All right, now that we've talked about this in theory, let me give an actual example of where it's used.